Welcome to short training video on ADS 2011 and EMPro 2011 version of linkage and integration, allowing people to transfer designs from one tool to another for purpose of various simulations. In terms of ADS and EMPro integration, there are two types of design transfers which designers can do. Number one, exporting ADS layouts to EMPro, whereby the entire material information along with the substrate, stack up information, etc. gets transferred to EMPro for very easy setup of simulation. Part number two is to import the EMPro based 3D structures into ADS for performing FEM based simulations in ADS layout. This video will demonstrate the first process, and that is to export ADS layouts to EMPro for performing full 3D simulation using either FEM or FTTT simulator. In order to allow ADS designs to be transferred to EMPro, we need to set a variable in a configuration file as shown on this screen. And the variable which needs to be set up is also shown on this slide. The care, however, must be taken to enter whether it is Win32, which is essentially for 32-bit OS, or Win64 if it is a 64-bit operating system. Now let's watch the video to understand the whole process, which should make it very easy for designers to understand how to do this kind of design transfer and very nice seamless integration between the tools. We will begin our demonstration by taking the simple patch antenna design in ADS layout, and as can be seen is a single patch element, and there is one pin which is connecting at the feed point. If you look at the substrate, we have set up the substrate using this new substrate editor window in ADS, making it very easy to define no matter how complicated is the substrate. In terms of dielectric material, we have a 62 mil height dielectric, and the conductor is defined as 35 micron of thickness, which is equal to 1 ounce of copper or gold depending upon which conductor has been used. If we go and observe the material property window, we have conductor 1, which is currently used in this design, and it is defined as conductivity of 5.8 e raised to 7, which is typically a copper. If you go to dielectric, the material which we are using and the name which we have provided as Rogers, having dielectric constant of 2.2 and loss tangent of 0.0023. Now once the substrate definition is set up in ADS, we can go to EM setup window, and it's very important to select FEM as the simulator instead of using momentum microwave or momentum RF. This is essentially a method of moment space simulator. Once we select FEM, we can go to Options tab and set up the option in terms of lateral extension, where we need to define the boundary of our geometry for 3D simulation in terms of X and Y, which is essentially lateral, and vertical in terms of Z direction. Once we set up these things into ADS, we can simply go to options called Tool and launch EMPro for import this design. Now, if EMPro is installed in the same machine as ADS, we can click this option, and once the variable is set in the configuration file, essentially it will launch EMPro and import this design along with the material property. If EMPro is not installed on the machine where we have ADS, we can always select this option of creating a self-contained import script, which essentially is a Python script, which we can then run in EMPro for offline structure construction based out of ADS design which we have done. So in our case, we have EMPro installed on the same machine. So let's click on this option. And now if the variables and all other settings are okay, ADS will export the design file and launch EMPro so that we can import this design into 3D platform from Agilent Technologies. So we'll wait a while till EMPro comes up. It usually takes few seconds on my laptop to come up. And once the EMPro is up, we can see all the settings and all the material information etc. will be imported automatically by EMPro. So now the structure is up. We can see the structure got imported successfully into EMPro and we have a successful message. Now if we move around in EMPro, we can see there's a finite lateral extension boundary as we define in ADS setup. And please note, all these things can be changed in EMPro, so it should not be thought as if these are fixed and we cannot change these parameters. Now in terms of con layer, we can see the patch exported from EMPro, from ADS, excuse me, and we have close bottom which is defining our X and Y extents. In terms of substrate, if we switch on the visibility by going right clicking and switching on set visible, the substrate has two parts to it. One is called as top, which is essentially the Z direction air definition. For this particular simulation, we will not need it. So let's right click and delete it. The another one, substrate layer 1, is the actual Roger 62 mil substrate on which our patch antenna is located right now. There is a warning message which shows that port, which is a waveguide port, it's not on the simulation bounding box. And that's perfectly fine. When we set our simulation condition, this warning will go away. Now before we proceed further, let's save this project by a name in a desired directory. So let's take it ADS EMPro video. Once the project is done, we can export the design. We can start simulating this design for the desired purpose. Now once the project is up, we can go ahead and look at the boundary conditions which we have for this simulation. In terms of boundary conditions, we can see we have assigned plus X and plus Y, minus X and minus Y as all absorbing. The bottom Z is defined as PEC, which is essentially the ground plane at the bottom, and then we have plus Z, which is defined as absorbing layer condition, so that we can note the radiation pattern. Once we are done, we can go ahead and define the FEM padding to define the finite size of the simulation boundary. So X and Y, X lower and X upper, are defined as 0 and 0, which is essentially across the width and the length of this antenna. And lower Z we can define as 10 mm, and the upper Z can be defined as 20 mm, so that we can capture front as well as back lobe of this antenna. Once we click apply, we can see the simulation bounding box increases its size, and now this is the size of the structure which will be simulated by FEM simulation in this EMPro. Similar steps can be followed if we want to perform FTTD simulations in EMPro. Now after setting these two conditions, we can go ahead and observe the material properties to check whether they have transported from ADS correctly or not. In materials, we can double click on the corn, which is essentially the material used for patch, and we can see the conductivity is defined as 5.8 e⁻⁷. And if we click on substrate layer 1, which is the material defined for dielectric, we can check the permittivity is 2.2 and the loss tangent is 0.0023. In terms of appearance, we can change the colors as needed so that our design can look a little more clear in the 3D domain. So I changed the color for this dielectric, and the effect of that can be seen immediately on the imported object. If we need to change the extents and modify the dimension of these imported boundaries, that can be done pretty easily as well by going into model and con and observing the sheet body. We can double click on it and we can modify the extents of the structure as needed, which is from the original design imported from ADS. So this makes it a little more convenient for users to modify the geometry directly in EMPro instead of always going back and forth from ADS to EMPro. And this results in a lot of time saving for designers. So once our structure is set properly, we can go ahead and define a far zone sensor because we would like to see a radiation pattern of this antenna after our simulation is complete. To add a far zone sensor, we can simply right click on here and we can click on new far zone sensor, and we can define our theta and phi depending upon where all we would like to see this radiation pattern by entering the right values, as can be seen here on this window. In terms of properties, we can have multiple sensors, and we can provide a unique name to those sensors so that while plotting the results, we can be sure which sensor data are we trying to plot. So we can click on done, and we can see there's a new far zone sensor which gets added here. Similarly, we can even add near field sensors if we want to capture a field at particular offset in particular orientation, which is essentially a planar kind of sensor. So in this example, we are not going to use that. Now, in order to begin FEM simulation, and we can have a drop down box to switch between FEM and FTTD simulation here. So in this video, we are using FEM simulation. We can click on edit simulation setup button here, and we can define the simulation conditions. So first of all, let's get rid of this min and max frequency, and 1 and 8 gigahertz is as per my definition, which we have done in ADS simulator. Now here 1 and 8 is defined as sweep adaptive type and defined as 50 point maximum limit. We can add multiple frequency band for simulation if we would not like to do a very large frequency sweep, which will take some more time than required. In terms of field storage, we can either define a user defined frequencies, or we can choose to select all frequencies from frequency plan so that we can observe the far field pattern in the far zone sensor for all the frequencies which are which will be simulated by EMPro. In terms of mesh refinement, we can define the various property like stop criteria in terms of delta S, number of pass. We can define a particular frequency for the mesh refinement, or we can define some advanced level controls on initial mesh and doing some advanced level mesh controlling. For FEM solver, EMPro offers direct and iterative solving technique. Iterative consumes far lesser memory, but can be little slower compared to direct. Direct solver is a direct matrix solving technique, but it might consume a lot of memory. So choice can be made depending upon how much RAM is available in the machine. The order of the basis function can be selected as desired. And then for the simulator, we can go ahead and put some notes which will help us to remember what all simulation we have done in future. We can also name the simulator, the simulation by some name, so that if we do multiple simulations, we can identify what all simulation settings which we have kept performing that simulation. So now once we are ready, we can go ahead and click on this button, create and queue simulation, so that EMPro starts the simulation process. So the first thing which EMPro does is to gather the geometry properties, material properties, and port information. Once these things are collected and there are no errors found in those, the next step is to perform the meshing on this structure. In case there are some problem regarding to the structure creation, mesher may fail, and it might issue us a physical dump of the mesher failure report, which can be observed to check what's the problem in creating the mesh for the certain structure. So currently, depending on the problem complexity, mesher will take some time in order to come up with the first pass mesh, and then it will be refined as we go along in consideration of the mesh preferences which we might have set earlier. So while the meshing is done, we can observe the output log. It gives some useful information in terms of the widths and the machine name, when the simulation was started, what version of FEM engine are you using. So this can be very helpful in case you are not getting the desired information out of your simulation, and Agilent can help you to understand whether you are using the latest FEM engine in your software or not. We will pause this video and we will return when the simulation is finished. Now we can see the simulation is finished and the far field pattern at various simulation frequencies have been calculated. To observe the results, we can go to the result tab here, and from the simulation ID we can choose the frequencies, or we can plot a complete frequency, adaptive sweep, S parameter response, or VSWR response as needed. To plot S parameter, we simply select on S parameter, and currently we only have one port for which S11 can be plotted. For S11 plotting, we simply double click on this results here, and we can observe the S11 for this structure. We can use these marker tools to observe the X and Y values of this patch antenna design, and we can see we have a resonance happening at 1.16 gigahertz approximately. In order to observe the 3D gain pattern, we can again go to results window and this time select far zone sensor, which allows us to see the gain, E-field directivity, and few other options which we might have selected during the setup. To observe the gain, we simply select the gain and double click again on the gain pattern to see the 3D gain pattern on this structure. We can use these zooming icons to adjust the gain pattern for best viewability. In order to set the orientation and transparency, we can use these options bar here to increase or decrease the opacity of this gain pattern. The nice thing about this whole thing that it allows you to see the structure along with the radiation pattern, so that we can also observe the direction in which the radiation is happening. Using the field reader tool, it is possible to read out the gain at different locations in this whole 3D pattern. So as you can see, when I move my cursor around, the slider bar keeps on shifting in terms of amplitude, representing what is the antenna gain in that duration at that location. Once we do a 2D cut of this antenna, we can clearly see on a rectangular or a polar plot to observe the beam width and look at the radiation pattern in more predefined manner. Along with the gain pattern, we can also plot some other results such as electric field, and we can double click on electric field to observe the electric field distribution for this antenna. Currently, there are two things which are overlapped on this gain pattern here, and we can choose to remove the gain by first selecting the gain pattern and then clicking on unload, so that we only left with the electric field. Now we can again change the opacity of this electric field to see how is this field distribution. Because we have calculated the results for various frequencies, we can click on the drop down box in the frequency tab here, and we can choose the right frequency. If exact frequency is not available, that can be because of the fact that we are using the adaptive frequency sweep, which does not guarantee your particular frequency to be available. We have a very simple workaround in order to overcome this kind of problem. So right now, let's try to observe the field at some other frequencies such as 4.5 gigahertz. And when we say apply, it shows the field pattern at 4.5 gigahertz. And if we go and plot the gain again, we can observe the gain happening at 4.5 gigahertz. So if we go and switch to 4.5 gigahertz again, we can observe what kind of gain pattern is observed by unloading the electric field from here. So this is the gain pattern observed at 4.5 gigahertz. Hope you enjoyed watching this video, and this helps customers in doing the design transfers and simulations in EMPro. Thanks again.